C'est un professeur-chercheur à l'Université de Florence. Donc, je viens de rendre visite dans le cadre du programme Erasmus, mais il n'y a pas que ça. Puisque c'est un grand collaborateur du laboratoire depuis très longtemps. Et entre autres, il est co-encadrant, il participe à co-encadrement avec mademoiselle Sarah Drevi. Donc il va nous présenter quelques notions voilà, sur des systèmes dynamiques complexes, mais à travers des approches plutôt discrètes, donc surtout les approches cellulaires et en relation avec d'autres approches. Voilà. Merci beaucoup.
D'accord, bonjour à tout le monde. Désolé, mais je présenterai le séminaire en anglais, parce que pour moi c'est plus facile, surtout parce qu'il y a les slides en anglais, donc c'est difficile de faire la traduction. Donc, this course I prepared a lot of material that I will leave to you. Clearly, I try to go quickly through all of this, and the idea is to, first of all, to justify why we use approaches like cellular automata here. So this is an article I wrote for the Encyclopedia of Complex Systems that I try to summarize in this first lesson. Then I shall present you some remind about dynamical systems, chaos, abstractors. I think that you are already familiar with all of these, but so it was already prepared, so I profited to use it. And then in the afternoon I shall try to present to you the whole field or some aspect of fields of phase transitions in cellular automata. I mean, the stochastic equivalent of bifurcations that we meet when we study dynamical systems. And finally, I shall illustrate the topics that I'm working also with Sarah in these days and with Samira about chaos, synchronization, and control in discrete systems, which is something rather unusual because you generally associate chaos with continuous system, dynamic, the differential equations, and so on. Okay, so let's go quickly here. You can stop me and ask questions when you want. So this is essentially the project, the program of this small course. And actually, we are used to study physics. Clearly, I'm a physicist, so I speak mainly about physics. Most of the topics apply also to other problems. We used to speak of physics thinking to real numbers. Space is continuous, time is continuous. But actually, these are essentially models of reality. We do not really know if reality is continuous or discrete. No? For instance, there are people that, like for instance, Feynman, that thinks that real numbers that has an infinite amount of information in any tiny small portion of space, for instance, no? Because if you have to represent a real number up to the infinite number of digits that you need, then there is an infinite amount of information. It is, in some sense, it feels strange that you have to store all this amount of information in a tiny portion of your space. And also, quantum mechanics says since everything is discrete, in some sense it is strange that also time and space is not. But okay, the idea is that actually we always deal with models that we build and that then we study about reality. For instance, we talk about particles and then we represent them with a set of numbers. Or we talk about molecules and we think of balls and springs and so on. Okay, the other thing that we have to take into consideration is that our cognitive capacity, because we want to understand the reality, but our cognitive capacity is limited. We do not have an infinite power in our brain. So what we do is that we try to reduce every model to a small set of variables, because we can handle easily problems that have up to 5 maybe independent quantities Otherwise, we are unable to manipulate these symbols. And another good help is linearity. When we have linearity, we can easily forecast what goes on, because if we double the input, we double the output, and so on. Okay? And actually, if you revise all the models that you have studied in physics and also in other disciplines, you find actually that most of them are linear. Or we study a lot of methods for reducing a problem to linear representation, and then we study linear representation. Sometimes we have to add some strange ingredient, for instance, a gas. Let's take the model of a perfect gas. I mean, those made by balls, no? That interact only eventually with one with the other, so that we actually study one single particle in one dimension, no? And then we derive the law of perfect gas, for instance, and so on. But we have to also assume that sometimes outside the model this particle interacts, otherwise they do not thermalize. I mean, if I take a gas with all particles at rest, and I put just one particle moving inside, it has to communicate the energy to all the others, but actually the collisions are not taken into account in the model, in the cinetic model of the gas, because this is too complex. So I add some extra ingredients, say, okay, they share the common temperature, and then I'm able to derive the Maxwell-Boltzmann distribution of speeds and so on. On the other hand, computers are much more powerful for what concerns, for instance, following the equation of motion, say, of some million particles. But this does not imply that we have to understand what is going on. So we can take a problem, say a problem of chemistry or a problem of biology, write down the equation that physics says that every particle obeys in this model, put them into the computer. Now we shall see this probably in some moments. And then I can follow the evolution of the system. But this does not imply that I, as a human, is able to understand what is going on. I still need to take the computer, say, simulation, reduce it to a simple model in order to be able to understand. For instance, just for showing you a real example, let's take the Lennard-Jones gas, which is a very simple gas. I mean, each particle is said to obey to a function, potential function that goes like this. I'm sure that you have met this in, say, chemistry or in other courses. No, I just use a two-dimensional model so that it is easier to see. And the idea of computer simulation of this gas is very simple. You just advance the position of a small amount of time. Yeah? Then you compute the forces, and you update the acceleration and the velocity according to the forces. And I can show you a real simulation of this, for instance, just to appreciate what is going on. No, not this one. So I think, for instance, this one. No. Just wait. I have to change it then. I'm mirroring the display. Okay, so you should see. Okay, so for instance, this is a gas with, I don't remember how many, say 10,000 particles. Then this is in a high energy, this is the energy for particle. And essentially one corresponds to the boundary between having energy that allows particle to go in average very far or to stay bounded. Okay, so the this says very little, but I can start lowering the temperature. You should see that here the numbers are becoming smaller and smaller, and at a certain time when the energy per particle is about 1 or 0, you shall see particles starting to aggregate. For instance, here you start seeing droplets of particles that are going to aggregate.
The wood behind you is
the
point.
I have to this one. So see. Okay. So now you see here that droplets start forming because the temperature is lower below 0. So essentially this is the liquid phase. Then I shall continue lowering the temperature, and essentially I'm going towards a solid. You'll see that clearly this is very quick, so I should have done this slowly, but okay, you see now it's still liquid, no? So the shape keeps changing, and there is evaporation, some high energy particles going outside the droplets. Then if I wait enough, it will start freezing, so losing the almost round shape and behaving like a solid with a particle vibrating around the equilibrium positions and so on. So we can wait some second for allowing it to cool. So probably these two are going to merge together, you see. So now, so you see that the temperature is not so strong enough. No, it is enough to allow it to cool into a round shape, but probably when they are going to merge, probably they stay in some non-spherical shape or non-circular shape in this case. So you see, now temperature is low enough that it has no energy for reaching the circular phase typical of water drop or liquid droplets. So essentially, this is a solid now with particles still vibrating, and so for instance here now it may collide with the wall and start turning like a solid. So it is now described as a solid, say, using the 4 degrees of freedom in this case because we are in 2 dimensions. And so this is still the same program. I just lowered the temperature. But for us, we use at least 3 or 4 different models for describing this same system. When it was in the high energy phase, we speak of, say, perfect gas with the PV equal to nRT and so on. Use a model. Then when it is a liquid, we use another model. Now, for instance, we use a model in which you have a solid with, say, elastic vibrations, not thermal vibrations. And then when we reach the lowest temperature possible, where all particles are almost frozen, we have a rigid body where we use the model of rigid body. So you see that we as humans have to use different models, each of them described by a small number of data or number of quantities, just to describe the same problem. This is still the same Lennard-Jones gas as before. That computer has no difficulty in integrating in high or low energy phases. Okay, and okay, so the idea is why I'm saying that, because I'm trying to justify the idea that that we use models. Okay, so there are models that you can use. This is a quick review of what I have shown now. And so, for instance, this is the description of the distribution of velocity in a high energy phase when it can be approximated by the model of a perfect gas, liquid, solids, and with the vibration, and for instance, the thermal expansion of solids. These are all models, different models that we use in order to describe the same system. And so the idea is that the real system is described by, say, if there are 10,000 particles, each particle has a position and velocity, 2 dimension, so we have 40,000 equations, so quantities related by equations. But we cannot deal with this huge amount of data, so we used to project the problem on a smaller surface, a smaller space, say, just considering slow quantities, like for instance pressure, temperature, and so on, and considering the fast modes as noise. This is the typical approximation that we do. Actually, it is a deterministic system, chaotic. So what we say, okay, we say there is a small number of variables, say the coordinates of the center of mass of the system, or the velocity of the center of mass, and the rest is a noise. And sometimes we disregard completely noise, and this is the field, the method of approximating a system, say, with the differential equation. When we approximate a real model, so a real system, say, with an enormous amount of variables, with a simple differential equation, you are considering the slow modes, not because you don't follow the fast moving particle, you follow, say, the center of mass, which is moving very slowly, and you disregard noise. Then you may add noise, and you have, say, stochastic differential equations, or you can use stochastic methods, like, say, Markov equation, and so on. No? Okay. So, for instance, the dynamical systems, a system defined as a vectorial differential equation, no? And a certain number of differential equations are representations in which you disregard completely the noise. And as we shall see in the next lesson, we are interested, for instance, in bifurcation when a certain solution becomes unstable and another solution appears, and so on. For instance, a very simple example of bifurcation, but I'm pretty sure that you are familiar with bifurcations, so on, or not. Okay, maybe we shall revise. Okay, for instance, a kind of bifurcation is this of the logistic map that we can explore quickly now and then revise in the following lesson. I use logistic map because I don't remember what I did. Because it is simple. Instead of having a differential equation, I have a difference equation. So I mean that the time is discrete. So I can have a lot of interesting behavior also in one dimension. While I shall see the next lesson that in one dimension the number of possible behavior of a differential equation is rather limited. So the logistic map is defined simply as this equation here. The variable, you may consider x is, say, the number of animals living in a certain zone. So the number of animals, they live, they lay egg, then they die, for instance, and the eggs in the next season will give birth to new animals. Okay, so the number of animals, with respect to a certain maximum number, at time t+1, it depends on how many animals are in the previous time, in the previous season, but also on the available space. So say that at maximum we can have, say, 1,000 spots where laying eggs. Now there are 1,000 trees, so each animal, each bird has to choose one tree in order to make his nest and lay eggs. So at maximum we can have 1,000 trees. So if the population is near 1,000, so divided by n is near 1, there is a much less nest free than when there are very few animals. Or maybe the limitation can be the food available in the territory. So when x is very near to 0, you can disregard this term and you have the classical exponential growth of an autocatalytic system. Say each animal lays a egg, and so you have a times the previous number of animals that were there. But when the number of animals is near the maximum capacity, here 1, you have less food, so actually the number of eggs is reduced by this factor, which is quite reasonable, no? When it is when you use this for the continuous growth, so using differential equation, this is called the logistic equation that grows and then saturates. And when and so in the 70s, Robert May say, okay, one animal do not lay continuously eggs, for instance. They lay eggs at a certain time and then they pass to the next season, for instance, insects. And so he studied this discrete equation. So how can I study this? This is the curve described by this part here. It is a parabola, like this. Clearly, x equal to 0 is at 0, x equal to 1 is at 0, and according to a, it may be larger or smaller. We can see it live in the other. Here. So I can change the number of eggs laid down in each season, and you see that the parabola is going down. Oh, let me change this from from 0 to 1 instead of from 3. Okay, so say clearly, when the number of x is very small, you say if it is less than 1, as typically if the total population is decreasing in time, because if you like for us, for instance, in the Western world, if we get birth to less than 2 sons per couple, the total population is declining because you don't replace the old one. So you see here what happens. I can start with a given population here, then I go to the curve in order to know how many are in the next time step. Then you go to the bisectrix in order to report this on the x-axis, because you have to iterate. No? So say you start from x equal to, let me here, with about 0.4. Then you see that the next is 0.3. For iterating again, you have to report 0.3 to the x-axis. The simplest way is to go to the bisectrix, no? And then to go to the curve. This is the value of the second degeneration. And then you go here, you have the third degeneration, and then the fourth, the fifth, and so on. And you see that if a is less than 1, the total fate of the evolution is going to be 0. It's going to be extinct. When a is larger than 1, no, not this. When a is larger than 1, No, there is a bifurcation. I mean, the 0 becomes unstable. I mean, if I start very near 0, it goes increasing. If I start larger than 0, it can be decreasing, or it can jump here and then start increasing again. There are a lot of possibilities. So, see, if I start here, it goes decreasing, but if I start here, first there is a jump and then it starts increasing again. And there is another fixed point. So I see that there is a bifurcation in this case, because first I have a stable fixed point in 0. For a equal to 1, it becomes unstable, and the new stable fixed point appears here. Then I can keep increasing the number of x. Here you can see the time evolution of the population. You see, okay, it simply goes to a fixed point. And here is the probability distribution of the population. Clearly, it goes to a fixed point, so you have only one peak corresponding to this value. You keep increasing the reproduction rate. At a certain point, something, you see, appears. Instead of having a fixed point here, I still have this fixed point, but now it is unstable, and instead it appears an oscillating behavior, which is really what is observed in reality. And so in many cases you have a population that keeps going, so one good season, one bad season, one good season, one bad season, and so on. And clearly the distribution now has two peaks, and you see here what is called a limit cycle. I mean, for whatever initial condition, I go to the same limit cycle, maybe after some transient. Okay? Then, if you keep increasing A, you have at a certain point here.
Double the period.
Yes, you have a double period, so the population maybe here maybe 4 times. So you see that now the population is still periodic, but it has more and more oscillation. So instead of having a period 2, you have a period 4, or you may have a period 8, and so on. Clearly, here you see also the transient here. So maybe if I am able to jump directly in the limit cycle, maybe I have to reduce a bit this. See here, you can see that now, okay, if I jump directly in the limit cycle, you see that this period 4, because I have 4 peaks in the probability distribution. And at a certain point, what is new here is that the system becomes chaotic. I mean that if you start, if you see this series, it looks still a bit periodic, but actually it is not, because it changes. If you look at the distribution, you have a widespread distribution. If you look at the trajectory, you see that it fills a zone instead of repeating itself. And what is more, I have not shown here, but if you start with 2 initial conditions, they diverge. Instead of going to the same attractor, they now diverge. And for instance, here is the maximum cost for this map. I can increase the length of the time series so that you can see that the probability distribution now is very widespread. Actually, it covers the whole interval here. The series is regular, and here you see that you fill the whole part. Okay, so this is an example of bifurcation. Clearly, you can visualize it in another way. In this way. Okay, now this is the same system, But now I'm trying to visualize the whole behavior in a single image. What I do is, for each, here now I have the parameter A, the one that I was changing in the previous simulation. For each values of A, I start the simulation. I throw away, say, the first 100 time steps in order to get rid of the transient. And then I plot other, say, 100 points. So clearly, you see that here is 1. So up to 1, there is only one fixed point, 0. Here is the value of x after the transient. It means that I started with a random value, but if you start going and then it goes to 0. Here you have the first bifurcation. I mean, the 0 is still present, but it is unstable now. If I start on 0, I keep staying on 0. But if I start just, say, 0.001, then I increase and I go to a certain value. So this is the first bifurcation. Here is the second one, that when this fixed point becomes unstable. So you may imagine that here there is still the fixed point, no? But it is unstable. So unless I start exactly here, I cannot stay in the fixed point. Now it appears the period 2. I mean that the trajectory is oscillating, and then you have a period 4 here, and then a period 8 and so on. I can show more in detail, for instance, this reason. You have the period 2 that becomes the period 4, that becomes the period 8, and then here you have a period 16. This is the period 8, period 16, and period 32, and so on and so on. Yet then you have chaos. You may have periodic windows. So the problem is really complex. You can have say it's a chaotic zone, and then a periodic windows appears. And actually, the periodic windows are dense in the chaotic region, because if you enlarge, for instance, this zone, you see again a periodic orbit here, and a periodic orbit here, and then maybe if you increase this, you see that there are other periodic. So the problem is really complex, even though the system is described by just one very, very simple equation. And okay, so now the exercise that I propose you is the following. Suppose that this equation describes exactly a real problem. That you don't know the equation, but you may get the data from this system. So, I mean that you don't know that the system is this one, but you have this data. So I give you this data, and I say, what do you think it is behind this data? It's just noise? No? For instance, you can make a statistical analysis and you find this one. And you say, okay, if I interpret this as a random process, I have this probability distribution. But maybe it is not a random process, it is a deterministic process, maybe a chaotic one. So what can I do? I can try to reverse this. How can I get this from this? Since this is obtained by iterating a method, so I mean iterating something that on the next time step depends on the value of the previous time step, I can try to plot each value as a function of the previous value. Clearly, in the practice, I have to try as a function of the previous value, as a function of the previous 2 values, as a function of the previous 4 values. I have to try all combinations. But just to be simple, let's try to do this exercise. So, essentially, this is the original method. This is the time series. And this is what I get if I plot the time, each value as a function of the previous one. here I get this one, not whole, but the part that is part of the attractor. Here, if A is very small, I just get some points because it is going to a fixed point. So essentially, after the transient, I get just 1 point. If I have a period to attractor, maybe it is not yet. This I get 2 points. No, because it is oscillating, so I get 2 points. Then I may get 4 points, 30, so like 4, and then finally when I have chaos, I can get the portion, visited. And but now, what can happen? This is so quite a long time series. Is about 500 points. But what happens if I have just a few points? And the problem is that if I don't have a very long time series, you see that it is very hard to distinguish if this is, say, a period, say, 1000, or it is, for instance, a real chaos. Or suppose that I am not able to follow this experimental system, because, for instance, I cannot measure at every picosecond the position of a particle in a gas. I have to sample it, say, every second, every 2 seconds, and so on. So let's suppose that I am sampling the system every 2 steps. Now the curve, the double iterates of the map is this one. It is f of x. Not very difficult. This is now is since f was a quadratic equation, this is a 4th order equation, but not so complex. Then I am still able to see something here. But if my experimental apparatus is not able to follow the system very all the time, I have a very complex map, and if I don't have enough pointer, it is very, very hard here to see that there is a deterministic system behind my data. Clearly, if I increase the number of points, I can start recognizing some structure. So, in a sense, the message is, even though my data or my system is well described by deterministic systems, say differential equation, partial differential equation, and so on, in order to recognize this, I need, first of all, to be able to sample data very, very fast. No? And then I need to have a very, very large amount of data in order to be able to reconstruct the deterministic behavior of my system. And this is for one equation. Imagine if I have, say, million of equations, because my system is deterministic, like the Leonard-Jones gas, but I have a million of equations. Then I need this problem multiplied by 1 million, probably raised to the power of 4 million. So this is why we then sometimes skip the description of a system as a probabilistic using a probabilistic model, instead of always using the deterministic model. Because we are not really able to understand which is the essence. So either I go back to the first principle, I mean, using like in the Leonard-Jones, I just write down Newton equation and then I'm sure. But then I produce something which is not understandable because it is too complex. Or, for instance, I use some simple model. For instance, when I model the motion of a planet around the sun, clearly the planet is made by, I don't know, some 10 to the 50 number of particles, and the sun the same. but the scale separation is so big that the thermal agitation of molecules inside the planets, no, I disregard them with respect to the motion of the center of mass of the planet. In this case, I can describe the system using a 2-3 differential equation, because the phase separation is so big, and the thermal agitation can be completely neglected. Okay? Then, clearly, if the planet becomes an asteroid or becomes a breach in the space, I cannot forget, for instance, thermal agitation or other factors. Okay. So, here you can find all these material here. I also leave you the programs that are quite simple, because you can just run by yourself. You can play with them, and Sarah now knows how to run. And so, okay, so here is what I already said. And so finally, we have chaos. Chaos, say, can be seen as a non-periodic motion that can be used. So this is just for showing you that the material is present in the slides. And what is important, I have not shown here, is that chaos actually has some robust feature, even though it is related to unpredictability. It has some robust feature. For instance, you can transform the data. So suppose you have this series, no? And then you transform this, because your experimental apparatus is transforming the system, and it has some nonlinear behavior, so it saturates and so on. But actually, if you plot the return map as we did before, after making a transformation of data, you still recognize that it has deterministic character. It is not this one. It is some kind of transformation of this. But still you see, okay, it is deterministic, because for each value of x, I have a single value of the variable at the next time step. So indeed, you can do this, but now the problem is that if you have a very short time series, it is very difficult to recognize the system if your sampling apparatus is not so fast and not so precise and so on to follow the real system. If you increase the number of points, you start recognizing. But this is why, for instance, some science traditionally use deterministic approaches, like physics. No? While other science, like for instance biology, generally use stochastic approach. No? Now that biology, for instance, molecular biology, is becoming more and more able to have very long and stable data, it's becoming more and more using the deterministic approach, no? Instead of just a stochastic. Instead of just giving the probability of having something, now you can try to apply deterministic methods, so the ones that you studied, also to fields like, say, geography, engineering, the environmental sciences, for instance, meteorology. Meteorology used to be a statistical science, now is using the deterministic approach, partial differential equations, in order to forecast the weather. Okay. And so, for instance, this is a famous Lorentz attractor, and this is an example of chaos. I shall show you in a moment. But then the other approach is using a stochastic approach. For instance, using a differential equation, but where you have noise. This is the stochastic differential equations. Or using, say, Markov approach, a classical stochastic differential equation, probably the simplest one, is a random walk. You have just, say, the velocity is a random function, because every time you get a kick with some molecule in the water, you are thinking of, say, some particle in the water, some pollen grain in the water. which is continually clicked by other particles, and so it makes a random walk. You can write down, if you want, the discrete equivalent of this one, which is called the random walk. So essentially say the position at time t plus 1 is the position at time t plus a random increment that maybe say minus 1 plus 1 or something like this. And if you plot, this is time, this is space, these are two trajectories, they start from the same position. Clearly, they, after some time, they separate because the random components are different. Then, clearly, you can investigate this problem. We started so one of the main contributions was done by Einstein. And clearly, here you are not really interested in these trajectories because these trajectories depends on the random numbers, so they are unpredictable. But if you still have this program here in the material, if you repeat the simulation many times, you can get some pattern and see that all trajectories stay, say, inside this portion of space, so there is a very high probability that they stay here. Most of them are concentrated around the center, and if you make the probability distribution of this, you see that okay, you have something that appears looking something familiar, and clearly you study now the probability distribution, and if you increase even more, here you have, I don't remember, some 5,000 or maybe more, 10,000 particles, you see that you are approaching the familiar Gaussian that you expect. And then clearly you may now try to obtain the description of the system at the level of the probability distribution. So this is the Markov description of the problem. Say the probability distribution, the probability of finding a particle at time t, at time t plus 1 in position x, is given by the sum of all possible previous position of the particles, of the probability of finding the particles there at the previous time step, times the probability that the particle goes from y to x in one time step. The probability of having x conditioned by being in y. Okay, so this is a very, it looks very nice, but it is actually a very complex equation because here you have all possible positions. It means that even though y is discrete, like in this case, say you have 1,000 positions, this is a vector of 1,000 components. So it means that this is a matrix of 1,000 by 1,000 components. This is 1 million elements. And so, actually, this is a very, very high-dimensional problem. So, in general, it is impossible to solve, even though you can do some analytic computation. But in this case, the structure of this matrix is very simple. Suppose that you have the probability of staying, of moving is q. So, the probability of staying into the same site is 1 by h cubed. So, on the diagonal, you have the probability of staying there, because the probability of being in x, having been in y at time step minus 1, but y equal to x, so the probability of staying on the same point, so it is 1 minus q on the diagonal. Then q is the probability of moving, and say p is the probability of moving right, rest moving left. So, to moving right, you have to be at left before, so QP is the probability of moving right, and Q1 minus P is probability of moving left. And you see that in this case the matrix is very simple because it is a circulant. I mean, it does not depend on the row, it is a constant, it is just a repetition of the same row. And moreover, it has only a few in each row or each column, it has just a few elements different from 0. Okay, in this case, you can use some technique. One is, for instance, the Fokker-Planck approach. I mean, can be used when the number of elements on each row is very limited and near the diagonal, and the variation along the diagonal is very smooth. So it doesn't change very much the problem from one point to another point and so on. You may have a diffusion coefficient different from point to point, but not so different. In this case, you can approximate this by a partial differential equation, which is just very simple. It is the diffusion equation or the heat conduction equation, the Fourier equation. No? Where here you have the drift, here you have the diffusion coefficient, and this is the evolution of the probability distribution. And so, clearly here you are completely neglecting fluctuations. So you are capturing the average behavior of the system, and clearly you can solve this, and you have the Gaussian, moving Gaussian, and so on. Now, okay, this is one approach that you can use. The other approach is this discovering of first Boltzmann and then Gibbs, the equilibrium. So if you are in equilibrium, you may have some possibility of going farther than the Markov approach, which is in many cases is impossible to follow. What is equilibrium? Equilibrium is that you are in a situation that does not change in time. So this is a stationarity, and moreover, you are in contact, or you may be isolated, or you are in contact with something that keeps some quantity constant. For instance, you are in thermal contact with the reservoir, so your temperature is constant, your energy in average is constant, or you are in contact with the reservoir of particles, so the number of particles in average is constant, and so on. So the idea is, the idea that was recognized later, is that, okay, let's suppose that I don't need anything more than knowing what is constant in this system. So the constraint. So I don't mind knowing the dynamics of the particles. I don't mind knowing how they distribute. So I suppose that I don't need to know how they distribute in space and so on. Maybe suppose that I just need to know that say the average energy is constant. What can I do? I can look for the probability distribution which only has this information. So which is the most generic probability distribution that still has this information? So I have to define information. So the information for a probability distribution is something that has, so I suppose that is going from a maximum to a minimum. The maximum information is when you know that the system is here. So the probability distribution is 1 here and 0 otherwise. No? The less information is when I don't know anything. So the probability distribution is completely flat. Okay. So one proposal is this one. This gives actually the opposite of information. This is a quantity of ignorance. It is called entropy. So it is P log P summed over all possible values. So let's check. Clearly, this may be indeterminate if P is equal to 0. So you have to define what happens when P is equal to 0. But since if you make the limit of x log x, when x goes to 0, you get 0. You say, okay, I define a new function actually that is 0 if p is 0. Otherwise, it's p log p. So let's check. If I have just one x where p is 1 and all the rest p is 0, I have for all the rest 0, because 0 log 0 is 0 for me. In this only point, I have 1 log 1, so 0 again. So when I know for certain that something is here, my ignorance is 0. Okay. Then what happens if everything is flat? So P is 1 over, say, n, where n is the number of boxes of your system. And so you have 1 over n times log 1 over n for n times. So the first 1 over n cancels with the number of terms. N times 1 over n, log of 1 over n. Then, so the first term cancels with the number of terms. Here you have log of 1 over n, it means minus log n, but I defined it with the minus, so I have log n, which is the maximum. I can show by, say, Lagrange multipliers, that this is the maximum of ignorance that I can have. And now, what happens? Okay, I don't derive it because, but it is a simple exercise. So now suppose that you know something about your system. For instance, you know that the average energy is something. Then you have to maximize the entropy, the ignorance, with this constraint. You use again Lagrange multipliers, and you find the Boltzmann-Gibbs distribution of energy is an exponential. This is the function, the distribution, that maximizes my ignorance, still having the average energy for a given quantity. And then you can repeat this for any problem that you want. So for instance, if you have an average number of particles, then you can find the distribution that maximizes your ignorance given this number of particles. So, why it is so important? First of all, because the exponential distribution has a nice feature that factorizes if the energy is given by the sum of energy that depends on different variables. Suppose that you have the Lennard-Jones gas before. You know that the energy is given by, so your variables are all the positions and all the velocities. You know that the energy is given by the kinetic energy plus the interaction energy. So this is not separable because it has a very weird function. But this is separable. It's just the sum of each component of the velocity. So you know that the exponential distribution factorizes here because it is a differential. This one. And so the problem breaks down into several problems, independent. Actually, they are coupled by the fact that they share the same temperature as before. And so you can solve each component of the velocity separately. And then you are left with this problem, but which has half of the degrees of freedom of the original problem. So at least you have cut your problem into half. Then the other interesting feature of this approach is that since you have found this formal solution, only supposing that you don't need to know anything about the dynamics of your system, now you are free to choose another dynamics. You are not constrained to follow the actual dynamics of the original system. You can follow whichever dynamics you want. For instance, one that is much easier to be done by the computer. For instance, you don't have to follow the trajectory of each particle step by step for very small time step. You can just generate the configurations without caring about how they originate in the original system. And this is the essential of the Monte Carlo simulations, which is really a tool that is used everywhere. So the idea is to generate an artificial trajectory using whichever rule you want, but clearly you need to be sure that at the end it originates the right probability distribution. And then you can use it for generating artificial trajectories of the system. And you don't really want to compute this because it has, say, 1000 components. You don't need to compute this. You want to compute the average values of some observables. Say, how is the energy, how is the temperature, what is the position of the center of mass of the average position of the center of mass of my system, and so on. So you would like to compute this, but this would imply knowing the distribution, which has a 1000 component, which is not very nice. But actually you compute this, so you construct an artificial trajectory that you are sure that in the long tail limit follows this probability distribution, and then you compute the time average of your observable over an artificial trajectory. This is the essence of Monte Carlo simulations, which is again a Markov process. So there are some rules for constructing the Markov process in order to be sure that you have the right probability distribution. I skip this because you are probably not interested, but if you need it is in the notes here. So, and then for instance, this is the standard way of generating the process. So essentially you say, okay, given my configuration Y, I generate a new configuration X using some rules that are so recipe of the method. And then, okay, generally I say, if the energy decreases, I accept the new configuration. If energy increases, I accept this with something that depends on the temperature. And you can, now you have a tool that allows you to explore very, very large, very, very complex system with a relatively less investment in your computer, because you can use your laptop now to investigate really millions of particles with very, very complex potential and so on. Okay. What do you expect? Why? Let's come back quickly and then I stop to the problem of bifurcation. So we have seen that an interesting point in the simulation of dynamical system is bifurcation points, because which is where I think that something very strange happens. Now when I study stochastic system, I have something equivalent to bifurcation, which are phase transitions. In phase transition, something very strange happens. Now I shall show you a simulation with a phase transition. In particular, for instance, let me see if I have this simulation here. Not here, but maybe in lesson 3. Okay, I think that I have in the model library using okay, so this is a very, very simple problem. It is the Ising model. I don't know if you have already heard about the Ising model. It has a nice story. So, in the beginning of the last century, there was a problem of phase transition, because systems like, for instance, water, when you boil water, or a magnetic system, for instance, you take a magnetic system and it has some magnetization. If you heat it, so you put it above a heater or a flame, at a certain moment it loses its magnetization. At a certain temperature, it is called the Curie temperature. And people were not able to understand why they observed this bifurcation actually. Now this is a sudden change of behavior in a lot of systems. And actually they were thinking that the actual physics law were changing when you change the temperature. So Lenz, who was a German physicist, assigned this problem to his student, his PhD student Ising, saying, okay, let's study the simplest model of a magnetic system. So the simplest model is this one. You have spins that can stay here like this or like this. So you just two position, 1, 1 or 1 minus 1, and you have an energy between them. Say energy which is low when they are like this and high when they are like this, and then you have temperature. And okay, let's see if this simple model has a phase transition. I mean, phase transition means that if you have a low temperature, you see the formation of large patches of, say, this is a spin up, this is a spin down, say. At the end, you finish with all spins in the same direction. Okay, maybe that can take some time, but you end up with this. If you increase the temperature, you may see some small variation, but not very important. Essentially, it still is in the magnetized phase. Okay, this is like the how to say, well, the magnetic system that you use every day here, no? But if you increase the temperature at a certain point, there is disorder appears, and if you go to high enough temperature, you see that the magnetization goes to 0. And then if you decrease the temperature again, clearly you can again go to the magnetized phase, maybe on the opposite side, then maybe you can go there. It depends on the fluctuations of the systems. For instance, in this case, probably I'm going in the opposite phase. So clearly, if you take the temperature as your parameter, you have a bifurcation very similar to what we have seen before. It is a fixed point in magnetization 0, which becomes unstable, so it may go there or may go on the opposite direction. But while we have studied the bifurcation in the deterministic system, and here is the stochastic system, so it is not described by a single differential equation as we are accustomed to. So Ising studied the problem in one dimension, solved exactly the problem in one dimension, but the problem is that this model has no phase transition in one dimension. So Ising concluded his PhD dissertation saying it has no phase transition in one dimension, so it has no phase transition in any dimension. Then he left physics. He was a very good teacher, but he did not continue. And now, if you go to, say, Physical Review or Archive and you look for Ising, you see that there is an immense literature about the Ising model that still bears his name, although while he has essentially concluded in the wrong way. Actually, it was right that in one dimension it has no phase transition, but in two dimensions and more dimension it has. Okay, so the important point is that for performing this kind of simulation, I do not have to follow, for instance, the dynamics of the spins, so represent them as a dynamical system and integrate the equation of motion. I can just generate configuration, for instance, throwing away all the kinetic energy part, because I already solved this problem. And I can use very fast dynamics, since I am able to simulate here, I don't remember how many of them, so say some 50 by 50 particles in a very, very fast computer time. Okay, let me try to finish. There are a lot of other interesting arguments that I'm not covering here. For instance, disordered systems and networks and small system. These are all problems that are quite difficult. Small system, for instance, is a very small, I mean, too large to be represented by a few differential equations, but too small for being represented by the stochastic method that we have seen. So, for instance, proteins are a complex problem because they are too small for one approach, too large for the other approach, and so they are still unsolved the problem. We can simulate them, and it is still difficult to simulate them, but we have many difficulties in understanding them. And okay, so for instance, this is just a resume of which are the paths of physics. You can follow this using many starting points. So for instance, suppose you start from Newton's law, F equal to mass times acceleration. Then you can go to low dimensional, so start studying simple systems, say planetary motion like Newton did and so on. Now, so you can study trajectories, attractors, low dimensional clouds and so on. Or you can go to high dimensionally, so a gas, and then you can use molecular dynamics or partial differential equations. So you can follow this where I try to resume something that some approach that can be followed. And for the moment, I stop here so we can say relax a bit.
Okay. Time for coffee break?
Yeah, coffee break.